All right, so we spend most of our time talking about graphs of polynomials in 5.3, but just a couple brief things about graphs of polynomials here. All right, so we're going to start with some more informal definitions. Okay, if I'm looking at the graph of a polynomial, let's say it's, some polynomial, I don't know, maybe it looks like this. Draw something that kind of looks like this. It's got some bends and waves and stuff like that. There's a couple things that we can say here. All right, we know the end behavior is like this. Already talked about end behavior. We know the intercepts, right? The x-intercepts are actually, hold on. Let's be precise. Here are these x-intercepts right here. All right, we know the y-intercept. There's only ever one y-intercept. Talked about intercepts in the last video. But then some new things that we're going to talk about are these things. Right here, and right here. These have a lot of names, honestly. These are called turning points, primarily in the book. And turning points are also where local extrema occur. All right, local extrema, it's where they occur. Where local extrema occur. This eraser is so big. Where local extrema occur. I want to make sure to be really precise for you guys. And all it means is where the graph turns from going up to going down, or from going down to going up. Right? If we're going down and then we start going up, that's locally our minimum. You think about it like hiking too, right? If you're going up and up and up and up, and then you start going down, well, that was a local maximum, right? You were at a little top of something. Now, maybe it wasn't the highest point on the mountain. Maybe it's not a global maximum, but it's the highest point in that little vicinity or something, okay? So we have a property that connects turning points with the degree of a polynomial. Let's propertize that. A polynomial of degree n has at most, that's important, at most n minus 1 turning points. And that at most is very, very important, right? That means a fourth degree polynomial has at most 3 turning points. If n is 4, n minus 1 is 3. Right? So again, if we're looking at an example, fourth degree polynomial, maybe our fourth degree polynomial looks like this. This is an example with 3 turning points, right? Here, here, and here. But we've also looked at fourth degree polynomials that look like this. This one only has 1 turning point. All right. We could also have a fourth degree polynomial that looks like this. Only 1 turning point. All right, so be very careful that that at most doesn't tell you necessarily how many turning points it's going to have, but it does tell you something about it. So let's use this property by looking at some problems in the textbook. Okay, so we're going to look at number 39. For the following exercises, determine whether the graph of the function is a graph of a polynomial function. These are homework questions. If so, determine the number of turning points and the least possible degree. So is this a polynomial? Looks like a polynomial, right? It has the right end behavior. It's got some turning points in the middle. Nothing weird is happening. No asymptotes or anything like that. It has kind of looks like an odd degree polynomial. How many turning points are there? Well, it's kind of flat, but there's a little turning point here. Little turning point here. So for number 39 on the book, number 39 in the book, right? There's 2 turning points. So what's the relationship between turning points and degree? Well, if degree n, that means at most n minus 1 turning points. So the least possible degree, right? If there are n minus 1 turning points, that means the least possible degree is n. That's just a rephrasing. This is a rephrasing of the property on the last page. Very useful. And again, it doesn't tell you exactly what n is, but it tells you the smallest possible n. Because yeah, maybe this is least possible. Hold on, let me answer this. Least possible degree here is 3. It looks like a cubic polynomial, but it could be a 5th degree polynomial. We just don't know. Okay? We don't know. Could be a 7th degree polynomial. We know it's odd because of the end behavior. And we know it can't be less than a 3rd degree polynomial because it has 2 turning points, but we don't know anything more than that. Look at this next one. Is this a polynomial? Nope. It's an exponential function. It looks like an exponential function. Technically, we don't know whether it's an exponential function. It's not a polynomial because it has an asymptote, right? As we go to the left, there's a horizontal asymptote. Polynomials don't have asymptotes. This end behavior is like this. And I feel like I'm trying to impersonate a referee or something. Well, I guess this could also be. Anyway. Nope, not a polynomial. It's not a polynomial because there's an asymptote. That's the easiest thing to identify. Let's do one more. What about number 41? This looks like a hyperbola to me. It almost looks like a parabola, but notice how straight it gets, right? Parabolas are curvy. This gets really strange. It actually looks like a diagonal asymptote. So I would say this is not a polynomial function. All right, we can't end on that. Let's do one more. Let's look at another polynomial. All right, well, 42 is not a polynomial either. 43 could be a polynomial. Look at one of these. What about 37, right? What about 37? That's definitely looking like a polynomial. How many turning points are there? 1, 2, 3, 4 turning points. 4 turning points means this is least possible degree of 5. All right, so you could look at it that way. All right, that's it for this video. Good luck. Bye-bye.